I'm Jonathan Fuentes. I'm currently an undergraduate student working in the Materials Chemistry Laboratory conducting research, which is a part of the Materials Science Engineering Department. I'll be going over the research I have conducted, and which has to do with the effect of magnesium acetate on the formation of brucite on magnesium oxide surfaces. So, just to give a bit of a background check on why this research project was done in the first place. So currently, Portland cement is the dominant form of cement used worldwide. It is used for infrastructure such as buildings, highways, and so forth. And it accounts for 8% of the Earth's anthropogenic CO2. And this is due to the high heating process of Portland cement, and which produces the anthropogenic CO2. So some of the alternatives that have been looked into are replacing the heating process with other sources or using alternative material based cements, such as magnesium oxide based cements. So, the reason why magnesium oxide based cements have been looked into and studied are because of its carbon/carbon negative capabilities as when compared to Portland cement. But the primary challenge in using magnesium oxide as a binder is its low hydration rate. And because of this low hydration rate, it produces a low yield of brucite. And brucite is really important for the carbonation process. And this is what makes magnesium oxide itself. Um, this is what gives magnesium oxide itself its carbon negative capabilities and low carbon capabilities. So the incorporation of specific ligands can be used as as a hydrating agent, in which in this project I use the acetate, which can steer the kinetics and reaction pathways of magnesium oxide based binders, which would produce more brucite. And that's the goal of this project is to produce more brucite and uh, to understand how magnesium acetate works as a hydration agent to produce brucite on magnesium oxide surfaces and whether or not it will be successful in doing so. So some of the materials and methods used were XC2 experiments were performed by immersing magnesium oxide samples into magnesium acetate solutions. So small single crystals of magnesium oxide were immersed into magnesium acetate solutions. The precipitates were then characterized by using atomic force microscopy and Fourier transform infrared spectroscopy were also used to characterize the surface of the magnesium oxide crystal. Frixie program was used for geochemical modeling for the experiments conducted. So this was done before conducting the experiments to see how the experiments would play out. So the experiment parameters all use the same, all use the substrate of magnesium oxide. Of course, I want to see the differences between concentrations and what happens when you increase the concentration of magnesium acetate and how that affects the magnesium oxide surface itself. And this is kept at ambient temperatures because that is one of the issues with using Portland cement or the production of Portland cement is the high heating process. So just looking into keeping low temperatures or ambient temperatures at 25 degrees Celsius is an alternative to that heating process. And keeping a reaction time of 1 hour to 20 hours. So early stages of production of brucite. So here in the results, you can see that these are XC2 amplitude images of the magnesium oxide reacted with different concentrations of magnesium acetate. So you have a 0.5 molar, 0.1 molar, and 0.05 molar at 25 degrees Celsius for 1 hour. So with an increase of concentration, precipitates begin to accumulate, showing early stage morphologies indicative of brucite. So if you look at the first image of the 1 hour um, reaction here at the 0.05 molar, you begin to form round precipitates that begin to accumulate and form rod-like structures or precipitates, which can be indicative of brucite, as brucite does have several different types of morphologies, such as lamellar sheets or hexagonal lamellar sheets, rod-like or triangular precipitates. As these round and rod-like precipitates, as you increase the concentration, these precipitates begin to accumulate and form agglomerations. And that's what you can see here in the zero point 0.1 molar concentration of magnesium acetate. So now moving on to the zero point 0.5 molar concentration at 1 hour reaction time, you begin to see a bit more defined structures, taller precipitates, and that seem to be amorphous brucite in a way. So these are all early stages of brucite. XC2 amplitude images of magnesium oxide reacted with different concentrations of magnesium acetate at 25 degrees Celsius for 20 hours. You begin to see greater definition of these morphologies. So compared to the 1 hour to the 20-hour reaction times, you notice that all precipitates are already rod-like structures compared to in the 1 hour. The 1 hour, you have circular structures beginning to form rod-like structures. And in the 20-hour, you already have these rod-like structures beginning to form these subtle agglomerations of, um, of precipitates. So, and this is similar to what you already see here in the zero point 0.1 molar, and of course here in the zero point 0.1 molar 20-hour reaction. In the zero point 0.1 molar 20-hour reaction, you begin to see greater accumulations of these precipitates. So this precipitate here is very similar to what you see here. And when you increase the concentration again, that's when you begin to see high defined brucite hexagonal morphologies. And these are some of these precipitates are six-sided precipitates. So the geochemical modeling of the saturation index of brucite in respect to magnesium oxide dissolved shows the dissolution and precipitation relationship. So as you have the magnesium oxide being dissolved, you have brucite being precipitated. And at all concentrations of magnesium acetate, a supersaturated state is reached, enabling the precipitation of brucite. So to reach brucite precipitation, or to gain that, you have to be at a supersaturated state. And you can see this that all concentrations were able to reach a supersaturated state. Of course, even at the 0.05 molar concentration, you see that that has the highest supersaturation state and is able to produce a great yield of brucite, or significant amount. So looking into the geochemical modeling of the pH of the solution in respect to magnesium oxide, um, dissolved shows the higher concentrations of magnesium acetate results in lower pH measurements. So what is going on here is that at least as you decrease the concentration of magnesium acetate, you begin to form, you begin to have a lower pH, and this is due to the trapping of hydroxide ions and brucite precipitates. And that's what explains the um, differences between pH between the concentrations. And when looking at the FTIR spectra, it shows the presence of hydroxide functional group peaks, especially here for all three. Even the zero point 0.5 molar, although it's a small peak, it does have a peak, which signifies for the presence of magnesium hydroxide precipitates, which is brucite, on the surface of the magnesium oxide crystal. You also have other functional groups present, which are due to the acetate itself, which could be due to the not complete dissociation of acetate on the surface of magnesium oxide. So so what are the conclusions from this? Well, the AFM images, the FTIR, and geochemical modeling data shows the extent of the effect that magnesium acetate has on acting as a hydrating agent to dissolve magnesium oxide to form brucite at ambient temperatures due to a dissolution and precipitation process. So this goes back to a dissociation of the magnesium acetate and then the dissolution of the magnesium oxide crystal. And then the dissociation of magnesium complexes enables the precipitation of brucite at supersaturated states. So this allows for a greater abundance of brucite to be formed even at low temperatures such as used in this research that was conducted. Okay, thank you for listening.